Hi everyone, thank you for attending to my talk. So today I'm going to talk about the churn rate prediction. Basically, actually this is not a real churn prediction, this is kind of a quasi-churn prediction because we don't want to know when a user is going to churn away from the business, but we want to know when they are going to decrease their user activity. So I'm going to talk about the problem of defining the churn, what is churn for our business, and then I'm going to talk about a baseline model, which is a public paper published by a couple of university professors done for an British gambling company. And then I'm going to talk about the experimentation of what kind of steps we took to improve the model. And then at the end, I'm going to talk about the model's results explainability. As I said in the start, we don't want to know when the user is going to churn, but we want to know when he or she is going to significantly decrease their activity, and we want to understand what is important for the business. If the person is going to decrease their login counts, the number of bets that he is making, or the number of the overall amount of the bets, or any combinations of all this stuff that we have mentioned, and also the number of active days. So the initial approach that we tried were decision tree-based ensemble models, because I'm sure we all know that the best models for the tabular data are still ensemble models of decision tree-based models, or there are some later research indicating that the ensemble models of deep learning approaches and the XGBoost are performing even better, but we didn't try it before. So we have mainly used the random forest XGBoost and LightGBMs. LightGBM is very similar to the XGBoost developed by Microsoft. So in difference to the XGBoost, the splits are being done by the leaves instead of the trees. And this is the model that have worked the best for our research so far. And so the main reason why we chose this LightGBM was that it worked the best, but other pro benefits that have come along is that it is explainable. Even before diving deep into the Shapley values, which is in the second part of the presentation, it has by default feature importance. So it can give information like which feature has been significant overall to predict if the user is going to churn or no. So the results are interpretable, and the decision trees are really fast. And although it is not a big problem when you already have your model deployed, but during the experimentation, when you are trying lots of features and you are doing a lot of experiments, it is very beneficial to have a model which is working fast. And data pre-processing is much easier. You don't need to do any difference, like any scaling or any normalization. Anyway, the LightGBM is handling all of that. And also, just like the XGBoost, the LightGBM is not so prone to overfitting, which comes along with the random forest. So here are some metrics I'm sure we are all familiar with when we are dealing with a binary classification problem. It's accuracy, precision, and recall. But when we are talking with the people from the business side, we want to understand which metric we are more interested in. So accuracy, of course, goes out of the talk because we are dealing with like very imbalanced data. So the first thing that we really care about is the recall. So we want to know all the churn people so that our customer retention team can prevent that. But we also don't want to go all the way to the recall and sacrifice precision, because in that case the company will give out a lot of financial stuff to people who are not going to churn away. And then so it's not like they are equal, so that's why we didn't try to optimize the F1 score. We already had in our mind that the first one is the recall and the second one is precision. So the baseline model, the link is in the title. As I said, it's a public paper, and they've actually used deep learning models, which is very strange for me. I was looking for just another paper, but there was none. This was the only publicly available paper that I can find. And one of the reasons is that the data is very confidential. Not a lot of companies want to give out their data to an outsourced company to experiment on it, and then even if they give, they are not publishing their results. And actually, I'm discouraged to share a lot of information about the data structure and stuff, but I'll use this paper and the features so that you can know what kind of features we are dealing with. So mainly, they are using GGR, which is gross gaming revenue. It's in a way for a player, what is the profit, like how much money they got out of the betting. And then the bet count, the last login date, and the deposit amount. So these are the metrics that I had, and as you can see, they are really interested into the churn class, and the numbers that they've reported are just for that class. And we can see that around the F1 score is around 50 to 60. I think it's 57. And the best stuff that they got for the recall is 0.61, which is, as a previous colleague used to say, it's better than random, but it's not very good yet, and it's not something that the business can use. So some drawbacks of the baseline is that it was not very robust due to the seasonality, especially during the summer. It's kind of holiday for the bettors because most of the activity is happening during the autumn and spring. So the model that they have built and tested for different months is behaving very in a non-robust way. You can see this is the green is the recall and the orange is the precision. They are going down and up around 0.6 to 0.7. So even if you got a good model, if you want to use it for the next month's data, it's not going to work very well. And as I said, we are dealing with seasonality.
Right, so I'm just sorry to interrupt. So here you can tune it with the threshold, right?
Yes.
Which you kind of need a calibration.
I think even the F1, even if if we leave out the thresholding, because it's just sacrifice between recall and precision. If you increase your threshold, you are sacrificing one for another. So the F1 score is again very volatile. As you can see, the accuracy is increasing and decreasing. In the paper, there is another graph with F1 score. It is again volatile. So just thresholding is not going to be useful. Thanks for the question. So the version 1 that we have tried is just looking at the snapshot and giving into the light GBM. So we just look into our users and then we see what did they beat, like what kind of look at the metrics about the betting a month ago, and then we try to predict if they are going to churn or not in the next month. And most of the features were related with this framework called RFM. If you have been dealing with customer behavior data, this is like a very popular framework to look into the recency, the frequency, and the monetary. So for the monetary, we're looking into the bet amounts, the GGR, the deposit, the amount of money that they are putting on their account, some features about the withdrawal, what kind of money they are taking out, and what was the last time that they have bet, and how frequently they are betting. But other than that, we have been using legs. So not only we are to predict the t+1, not only we are using the t, we are also using the t-1, t-2, and so on. And also we have done some feature engineering to calculate the ratios for the nth leg. So we would divide the GGR of this month compared with the previous month to see if there is a growth of bet amount and GGRs. And I think at this stage we had around 45 features, and like based on those metrics and their interaction terms. So as I said, I'm not allowed to share the actual results. So I'll use this like version 1 as the baseline. This is like the vanilla approach, and this is the confusion matrix. I'm just like, there are some numbers, but I've put everything to 1, and then I'm going to talk about the other experiments and how the other experiments have given different results compared with this one. The only reason I gave the confusion matrix about the public paper is that it's publicly available. You can just find it in the internet. So this is like the baseline experiment. Don't confuse this with the baseline, which is the publicly available paper. And then the next step that I did, I looked into the panel data. I looked into the panel data to fix the problem of seasonality to make my model more robust. So instead of looking for the, let's say, June month, I've looked into June, July, March, and like 1 year ago, I took all the snapshots and I constructed panel data, which is basically a combination of cross-functional data and time series data. But this comes with its challenges as well. You need to make sure that the data splitting is done in a way so there is no data leakage. So instead of just doing data split between all the rows, like 80-20 approach, I did the same for the number of users. So I looked into the 80% of users' data, trained on it, and tested on the 20% of users. Again, not for the rows, but for the users' activity. Yeah. And another, what kind of problem, so I talked about the disadvantage, but what is the advantage? I have I've increased my data like 15 times, and this data is not just like another data, but I've looked into the historical snapshots. So in this way, my model will be much more robust. Yeah, and this is the results. As you can see, I have sacrificed some precision and recalls for the active class, and actually my precision of the churn class has decreased around 7.5%, but I've got a huge boost in the recall. So like around more than 50% increase in the recall for the churn class. And to just give it into perspective what this number is around, my version 1 didn't beat this baseline, but my version 2 was already good enough to beat the baseline in terms of both the recall, in terms of the recall and the F1 score. And then another experiment that I did, I'll try to talk much faster as I'm a little bit behind. So I've done another two approaches. One of them is to look into the sports data differently and into the casino data differently. So when you are playing, when you are betting, you can either play in an online casino or bet on sports, like yesterday was Turkey-Armenia game. You can just go and put money on who is going to win, or you can just play a video slot. And those games are like, and the user activity between those categories are very different. So if you want to squeeze everything into one metric, it's not going to work very well. And then we have also used the number of bonuses that we have given to the users and how much is actually have been used. And after that, we have seen a little bit increase into the recall to around 60%. And we have actually beat the baseline for the precision after this. Again, and the next like experiment that I did, I started to look into each feature separately and to look also the distributions for the false negatives. So I saw that some features, like the bonuses, they are significantly increasing the false negatives. So I started to talk with people who have domain expertise another time, and then we understood that instead of using the bonuses, we shall look into the data of the number of days a bonus has been used. And this comes again because we have like a lot of games, like thousands of games, and those games categories are different, and their user behavior is different. So if he's playing one game, he can play 50 bonuses, but it's like around the same if he played if he played a game from the category 2, where he can just like use one bonus. So again, because the games are very different into their like rules, I shall take this into account into my features. After doing some more feature engineering, I've increased the precision like with more than 1/3, 1.37. Again, this is the growth compared with the experiment number 1. I think this is the current state of what we have, and this is already something that the business can use. And then I'll talk about the feature importances. So as I said, we've been using two methods. The first one is the vanilla approach from just using the feature importances from the light GPM. And by the way, one common thing is to look into just the splits, but I prefer to look into the information gains. So basically, there is a parameter where you are like looking into the features. So if you are looking into the splits, you are using how many time feature has been used to do a split. And then if you look into the gain, this is not just the like average, but this is like weighted average kind of. So it looks into each feature, and instead of like giving a count how many time a feature has been used, it is looking how much information the user like the feature has given. And you can see some leaked information about our features, what kind of feature we have used. L ratio is login ratio, recency, like how many days ago the player has played, unique bonus days, 1 means leg, and stuff like this. And then we just like instead of just looking into the absolute gains, we are looking at the relative importances, so we can see the share of each feature for the model. The next one that I want to talk about is Shapley values. And so I'm coming from an economics background, and this is something that has been used from 1953 in economics, specifically in game theory. This gives a framework of how to fairly reward a person who is playing a game. Let's say there are 5 players in basketball team, and then you want to look and then you won the game, but you want to reward based on their performance. So one way to do is hypothetically we are saying, what if this player didn't play, and then what if look into the prediction, what would be the performance of the team if player number 1 didn't play, and then you'll look into the performance of the team if player number 2 wouldn't play. So just to give an intuitive thing, what Shapley values are, they are coming from the cooperative game theory, and then Shapley values is trying to give a fair distribution of rewards. So let me try to bring an example. So you have this example of predicting a house price. Everyone has played with the Boston dataset, and then you are looking. You want to predict what would be the price of a house if it had some green areas inside. It was in the second floor, and it had 50 square meters of area, and then the cats are banned, so you cannot keep a pet in that area. So you look into the data, it's $300,000, and then you are looking into other rows of the data set, and then you are trying to find what if all the approaches are the same, and you have first floor, the cats are banned, but in the second one, you see what the model would predict, and then you can see that if you allow the cat to be used in the house, the price of the house would increase by 10,000. So what you can do to calculate the feature importance, you can just look into all the rows, and then you can look into the marginal contribution of each feature. So basically, you are just going through the combination of all the features. So first you are looking at the model if there was no feature at all, and then you are looking, and then you are trying to predict the price of the house just by looking if there is a park nearby, and then area is 50, floor is in the second one, and then you are looking into the combinations of those features. And then for each of these coalitions or combinations, we compute the predicted apartment price without the feature of the value of the feature called cat band. And then we take the difference to get the marginal contributions. And basically, Shapley values is the addition of the weighted average of all these marginal contributions. So I will not dive deep into the mathematics behind the Shapley values. I'm already behind the time. If I were on the time, I would still not be able to do it. So the intuition is that we are looking at the feature values that enter a room in a random order. All feature values are in the room participate into the game. So you are looking into the contribution of prediction, and then Shapley value of a feature value is the average change in the prediction that the coalition already in the room receives when the feature value joins them. So you just look all the cases with the before, all the cases where you use the combination of those features, and then you take the average when you add the cat band. So why do we use the Shapley values at all? I think they have two important areas where it helps. First one is it can give you a role-based explainability, how much each feature has contributed to the prediction. So instead of saying, this player is going to churn away, we are saying this player is going to churn because the number of logins has significantly decreased. So don't just do like simple giving a bonus to a person, but do a personalized bonus to increase their login count. So in this way, our customer retention team can design different strategies to keep the user in the platform. So again, it's because of personalized recommendation, and then we can rank the feature for each user. And the second one, so the first one is the what is the benefit of Shapley value for the business. For the ML team, you can use it for monitoring to see if there is any significant change in what Shapley values are. So it will give you insights if there is a specific thing changed into the business. In my previous company where I was employing a similar approach, at some point some of the features that we have been using became obsolete because they started not to do the business the way before, and like the churn output has completely changed, the distribution has completely changed. But if you look into the Shapley values for each different features and then you look into the history, you can see like this is the guilty feature, take it out and look what changed into the business, bring up with a metric that will map the rule of the game into the model. I guess this is it. I guess I run out of time.
Yeah, let's say you have two features, cats and location. And let's say in one location people love cats, and in another one people hate cats. And so these two features are dependent on each other. How do you deal with when two features depend on each other, and sometimes feature of having a cat is a bonus, it gives a positive value, whereas in some other location it gives a negative value.
I think, so Shapley value is not the only way of looking into the like contribution and explainability. And one of the drawback of the Shapley value is that, it assumes they are independent, which is not always the reality. I think there is another approach called Lime, if I'm not mistaken, and then it can, I think it can help you with this case. And also another drawback of the Shapley value is that it will not help you to say if the house, instead of being 50 square meters, if it were 70 meters, what would be the prediction? It just looks if there is this feature, yes or no, and then looks into the marginal contribution. So those approaches have their own benefits, advantages and disadvantages. I mean, it would be much easier if we just use the linear regression model where we have coefficient and everything is perfectly explainable. But they don't always, they mostly don't give as much accuracy as decision trees and ensemble models provide.
One more question. In managerial economics, the establishment of the price is set up by long formulas. For example, what is the end price of the product, for example. Now I would like to, in your model, for example, defining the churn rate of the customers and the churn rate of your workers, for example, of the company, it could be done in a formula, for example, which adds 8 main metrics and the combination of the features gathered in clusters. For example, with such a formula, we can define the churn rate of the company for the last 1 month, 2 months, or the next 1, 2 months, and so on. Can we do that?
I mean, the simplest and easiest way is just to come up with a linear regression and come up with 8 features. But then, I mean, it depends on the pricing model. I mean, it's not what you described is cost-based pricing, but then there is also value-based pricing. So, for example, I have the same Apple, and just like in the SaaS market, I'm using Spotify, I'm paying $5. Someone who is in US, they are paying $10. So there is also the cost. It's not, so what you described, the process is a cost-based pricing. And in that terms, I'm sure they are just using a linear regression or an extension of it. So to answer your question, yes, you can. But it's not the only scenario how pricing is being done. Thank you.
What is prevalence of churn class in general population?
I'm sorry?
What is prevalence of class 1 of churn class in general population?
I know the answer, but I'm not sure if I can disclose that information. I'm sorry.
Because you showed metrics precision and other, it is very important to know the prevalence.
It's highly imbalanced, let's say. It's around 10%. But then we are also dealing with, I think this is another thing that we shall discuss. It's not like a player has churned in this month, like we lost him completely. He can come back next month. So it's a recurring event.
Or did you somehow deal with these class imbalances?
Yeah, I mean, there are the oversampling or undersampling, but my favorite way is to just take it as a given that the classes are imbalanced, and then instead of maximizing the accuracy, maximize recall and precision. And as I said, with the business, we made a decision to maximize, first of all, recall, but also care for the precision as well.
I see, thank you.
Any more questions? Let's thank the speaker again.
Thank you.